All right, well, good afternoon and happy St. Patrick's Day. And thanks so much for joining our Collins Aerospace webinar on future vertical lift with a specific focus on weight and drag. My name is Al Kilfer and I'm a member of our communications team. We've got everyone set to mute, but you will have an opportunity to submit questions during our Q&A at the end. And we encourage you to use the chat function to do that. Also, this meeting is being recorded, and we'll have 3 poll questions throughout the course of the presentation. Obviously, there's no right or wrong answer. We just encourage everyone to take part in those. So now it's my pleasure to introduce our host for today, Luke Schmidt. Luke is our Director of Military Strategic Pursuits, and he leads our Future Vertical Lift strategy capture. Luke began his career in the U.S. Army as a Kiowa Warrior aviator, spent 11 years in the U.S. Army, and joined Collins Aerospace in 2016, where he spent the past 5 years in various leadership, program management, business development, and strategic roles. And now it's my pleasure to introduce Luke. Luke, over to you.
Well, thank you very much, Al. It's an absolute pleasure to host this event today, and it's an honor to serve in a capacity at Collins that benefits our warfighters and provides cutting-edge technologies to the Future Vertical Lift program. Today we're going to focus on a topic that is near and dear to all of us that serve in the rotary wing space, and that's weight and drag. At Collins, we know this is a key success factor, and we want to share some of the initiatives we're conducting on this topic. Before we jump into that topic, I would like to share a little bit more about Collins Aerospace. As the FVL capture lead, I help coordinate across our 6 strategic business units at Collins. And over the past couple of years, we've experienced some change. And I'd like to start today with just a brief overview of our organization, which we'll show on the next slide. What you see in front of you is our 6 strategic business units that make up Collins Aerospace. We were formed in 2018 when UTC Aerospace Systems and Rockwell Collins came together. And as of this past April, we are now one of the 4 divisions of Raytheon Technologies with the merger of United Technologies and Raytheon. So the 6 strategic business units, they offer a wide breadth of capability, from aircraft structures to seating to rescue hoists, and all products that help pilots aviate, navigate, and communicate. Our comprehensive portfolio across these businesses allows us to lead the way in innovative, technologically advanced, and intelligent solutions. And you'll see a number of those examples from our businesses today and exactly how we're doing that for the Future Vertical Lift program. So now as we transition to the agenda, this is what we'll be working to today as part of our presentation. We've identified key themes as we look to support the Future Vertical Lift program, and I'd like to walk you through those. Weight and drag are key focus areas at Collins, and in an area that we continue to concentrate and invest in as part of our new product development for Future Vertical Lift. We'll take about 20 minutes to walk through those first 3 agenda items, and then we'll transition into a question and answer session. And even though we're starting in presentation mode, like Al mentioned, we want this first part of the session to be interactive as well. So we've established some poll questions, through the presentation, and I really look forward to your real-time feedback on these questions. So with that, let's dive right into our first topic. Collins has been working on the FVL program for over the past 10 years. We've dedicated resources to develop solutions with the goal of exceeding the expectations of the program. And there are 4 key themes that we believe are critical to doing just that. First, investment. Investment in innovation and the Army's overall modernization priorities. We believe to be successful, this program needs long-term partners that are in it for the long haul. And at Collins, we're leveraging years of experience with the Army to apply ready now and future capabilities over time and across modernization efforts. We're leveraging our commercial investments to apply innovative advancements to those priorities. Second, we're committed to an open systems approach. That's how the Army is building a truly best-in-class Future Vertical Lift ecosystem. It allows for greater mission flexibility as well as easier, faster advancements as new capabilities are integrated into the program. We're working in lockstep, with the Army and with industry to ensure this objective is achieved. The Collins Open Systems architectures provide best-of-breed capability and commonality for the full spectrum of future vertical lift requirements. We've demonstrated these and fielded these open systems. We've implemented MOSA across a broad set of capabilities and product lines that we want to bring to future vertical lift. We're also aligning across many of the businesses inside of Raytheon Technologies, including Raytheon Intelligence and Space, Raytheon Missiles and Defense, and Pratt Whitney, to ensure that products work together and share a common MOSA. Third, we're building solutions that enable affordable and efficient sustainment. That means keeping maintenance ease and affordability top of mind. As well as building the roadmaps now and for how to advance the platforms over time and avoid costly updates in the future. We share the Army's goal that these aircraft must be successful, affordable, and adaptable for decades as they meet the demands of the modern battle space. And finally, optimizing solutions for weight and drag. This is a critical and a complex component so that we can deliver on power, speed, range, and payload capacity. And ultimately, it's a key success factor for the Future Vertical Lift program for both FARA and FLRAA. All of these things together are extremely important for the program. But as we transition but when we get down to the performance of the Future Vertical Lift platforms, delivering on the speed and range requirements that are going to enable overmatch, weight and drag is critical as systems and capabilities come together. So let's dig in a little bit further on weight and drag as we go through the rest of our presentation today. As an Army aviator is preparing to conduct their tactical mission, we need to provide them a great starting point. So minimizing the basic weight of the aircraft and drag of the aircraft are key factors in enabling increased capability. And that's a critical point, and that's the critical point of design that we find ourselves at today. That increased capability can come in the form of additional fuel, additional ammo, rockets, missiles, and additional speed and range. It can also come in the form of additional soldiers, gear, and air assault payload. At Collins, we take that challenge of reducing weight and drag very seriously in order to enable the aviators that will be executing these important missions. Some of the critical success factors of Future Vertical Lift, the things that will allow the program to deliver supreme performance and provide the warfighter with a state-of-the-art vehicle to stay ahead of adversaries are power, speed, range, and payload capacity. When you look at those success factors and how we're going to achieve them, well, you can achieve speed and range and payload capacity at the level needed without spending a good amount of time on optimizing weight and drag elements. With that said, we know it's not an easy challenge. And so we'd like to take our first poll question of the day, and that addresses this important challenge as we know this topic can be very complex. So as we take a look at our first poll question, I'd like to provide a little bit of context on what we're asking. We're viewing this question from a developmental perspective as well as from an aircraft that has already been fielded, and what are some of those key challenges that are around this important topic. For example, the emerging design requirements as airspeed requirements increase, the acquisition of systems, a federated approach versus an integrated systems approach, or number three, maintaining weight and drag optimization over time as capabilities are added, after an aircraft has already been fielded. So please take a couple of moments and respond, and we look forward to your real-time feedback. Okay, I think everybody can see the feedback, and I think it's expected, all three of these areas present challenges to us as we're looking at weight and drag complexities. So what I can tell you at Collins, we're working to bridge the engineering design of our products to improve the operational performance of the FVL platforms. We'll now discuss how Collins is addressing these areas as we transition to the next slide. Okay, so we view the weight and drag challenge in three key areas. Number one, the complex emerging design design and siloed systems acquisition. So there are hundreds of systems on board a military helicopter from a number of suppliers and from a number of experts. Identifying cross-systems optimization opportunities across the platform can be extremely difficult. You end up with too many boxes that are not optimized from a total system standpoint. Number two, revolutionary advancements in speed, endurance, and lethality. We're building the next generation of military rotorcraft to outshine any adversary and any platform that exists today. That in itself presents challenges for how we build this aircraft. It has to be better than anything that we've done before. And number three, the evolving battle space and sustainment. We don't have a crystal ball, but what we do know is that the battle space is going to continuously evolve. Mission environments will become more challenging, and we have to build a platform that stands up to those challenges and can evolve over time. And we don't want to do that with adding boxes and components that will pile on weight and drag, and additional time for integration of those components. And as we consider components, we must understand the different types of drag that a helicopter experiences. So as we transition into specific ways that Collins is addressing the weight and drag challenge, I'd like to introduce our second poll question. And for the aviators in the audience, this might be a quick check on learning. So as we look at our second poll question, we'd like to get your feedback on the areas of what three forces make up the weight and drag challenge. So take a few moments and provide us your real-time feedback. Okay, so if you answered induced, parasite, and profile, you get a gold star for today. Okay, and I've lost the screen here. Not sure what happened there. Okay. Okay, so as we look at integrated structures, that's one of the first areas we'd like to kind of talk about on some of the things that the Collins Aerospace is doing as we look at reducing weight and drag. We have a large breadth of systems and capabilities at Collins, and we're using our collective knowledge base to integrate systems across our capability sets. This is allowing us to gain best-in-class solutions at a fraction of the weight and drag. So as we look at the next slide, we want to take a little bit more detailed look at some of the things that we're doing from an integrated structures approach. We're focused on minimizing the size and number of apertures on the aircraft and integrating those systems into flight surfaces and structures, reducing what normally hangs off and causes drag. We're looking at significantly reducing parasite drag as we look at our collective antenna and lighting capabilities. We're investing in integrated antennas within the aircraft structure, eliminating drag entirely. We're integrating antennas and lights into a single component. We're using our state-of-the-art LED technology that is not only lighter in weight, but also requires less power. And the system can be flush mounted to reduce drag. And as we look across Raytheon Technologies, we're also finding innovative ways to bring multiple functions into a single aperture. In support of the FLRAA program, our hoist is built in a modular fashion. That modularity enables integration of key components such as the gearbox, the motor, and the controller in different configurations to fit inside the aircraft, thus minimizing drag. Our latest hoist technology, the Pegasus hoist, also has an increased load capacity of 11% without increasing any weight in our design. The final structural example that I want to share is our payload deployment system and weapons bay door design. We can internalize the weapons rails that would normally hang outside the aircraft and now putting them inside the aircraft to reduce drag. This system can go from fully stowed to deployed in less than 3 seconds. So this is just a glimpse of some of the product areas that we're focused on as we look to optimize drag. And as we look inside the aircraft, I'd like to transition to ask you our third and final poll question. And this is, we want to take a look at our pilot seating. So how much weight do you think we could save by using advanced materials and advanced structural design techniques for pilot and co-pilot seating? Please take a couple moments and provide us your feedback. Okay, so thanks for that feedback. Definitely no right answers here. It could be any one of these answers depending on the approach. But what I can tell you is the Collins answer is 30%. And that 30% equates into 48 pounds per seat, or 96 pounds across the aircraft. That's a lot of ammo, that's a lot of fuel, that's a lot of soldier gear that we can add in place of that saved weight. So as we go to the next slide, our interiors team is taking our leading commercial offerings to support the modern warfighter and missionizing their family of products. We are currently fielding a pilot and co-pilot seat on an international attack aircraft, applying our advanced materials and our commercial structural design techniques that provide that weight savings. Another area we're focused on is replacing metallics with composites to reduce weight in heavy systems like drive systems and flight control surfaces. These are areas we continue to pursue. In fact, we're using our braiding technology at our Composite Center of Excellence in Banbury to reduce overall production costs and maintaining high quality and reliability. And finally, our aerostructures team recently completed the development and test of a redesigned, lighter weight by 15% F-16 horizontal stabilator using our resin pressurized mold technology. And we are currently developing thermoplastic manufacturing methods to support fixed wing and helicopter control structures to enhance durability, lower costs, and reduce weight. So these are just a few of the examples of how we're looking at advanced materials and advanced designs to reduce platform weight across the Future Vertical Lift program. So now let's transition to the kind of the inside of the aircraft as we look at wiring, the size, and the amount of boxes in an aircraft. So the Collins Mozark system utilizes a robust, open, safe, and secure digital backbone. This infrastructure is critical in enabling further weight reduction of an aircraft system. This design is focused on high-speed, deterministic data distribution, allowing even time-sensitive functions to be integrated into the central network, eliminating wires by integrating functions into a common central network. Secondly, our vehicle management computer, the Paragon. The Paragon is 20 times more powerful than any existing flight control computer on the market. The Paragon is able to host multiple applications, eliminating dedicated boxes and wiring by using the computer's spare capacity. Our FlexLink system. FlexLink is an adaptive connectivity solution that consolidates the capabilities of multiple comm, nav, and data systems to reduce weight, and it utilizes a shared multifunction conformal antennas integrated into the airframe to significantly reduce drag. And then finally, our next generation vehicle health management system also has a 40% reduction in wiring weight by using a shared connected network and forming a common prognostics backbone. Again, these are just a couple of the areas that we're focused on in significantly reducing weight and volume on the aircraft. So that actually wraps up the formal portion of our presentation today, and just a quick look at some of the things that we're doing at Collins Aerospace to support this critical Army program with best-in-class solutions that are highly optimized for weight and drag. We have many more capabilities that address the needs of the program, from digital backbone to advanced comm and nav solutions and much, much more. We have a legacy with Army Aviation, and we're excited to continue to innovate and advance and help lead the way for the next generation of military rotorcraft. Now, I have a number of colleagues that have joined me today across our organization that also support the FVL program, and I'd like to just quickly introduce them as we move into the question and answer session. So first, Mr. Harold Tiedemann. I work very closely with Harold in his role as the Collins Aerospace Chief Engineer for Future Vertical Lift. Harold is a technical fellow with deep experience in flight decks, digital backbone, and systems integration. Mr. Steve Avrich is from our Power and Controls business unit. He's a technical fellow and a key architect of our Paragon, the vehicle management computer. Mr. Richard Bryson is from our Mechanical Systems business unit, and he's the chief engineer for our Pegasus hoist. Mr. Preston Johnson is from our Mission Systems business, and he leads U.S. Army business development activities. Mike Riley is from our avionics business, and he leads FVL pursuits across the avionics product lines. John Terrell is from our aerostructures team, and he leads military pursuits for aerostructures. And finally, Miss Joanna Ware. Joanna joins us from our interiors team, and she leads all military pursuits for the interiors product lines. So Al, with that, why don't we go ahead and kick off with our first question?
Yeah, sounds good. Thanks, Luke. Got a couple questions coming in here. First one is, we know Collins Aerospace has a long history in flight control computers. What makes the Paragon vehicle management computer so unique from anything you've done in the past?
Hey, Alec, that's a really good question, and I think I will defer to Mr. Averich for that one. Steve?
Sure, and good afternoon, everybody. So the Paragon Vehicle Management Computer has a number of new state-of-the-art features that distinguishes it from flight control computers of just a few years ago. So first is the sheer increase in processing horsepower. The Paragon VMC incorporates multiple quad cores, greater than 1 gigahertz processors. And the second sort of new feature of it is its approach to common mode failure mitigations. Generally in the military world, in the past, we haven't had a requirement for common mode failure mitigation, but in the civil world, we always have. And as the military world starts adopting more of the civil standards, common mode failure mitigation is going to become a key factor. So the Paragon already incorporates a number of those strategies, including numerous dissimilar functions, including the processors, FPGAs, backplane switch fabrics, and even functions such as something you might think simple as an Ethernet MAC. We use dissimilar devices within to guarantee no common mode failure can impact the performance of the box. A third feature is its reconfigurability. We all understand that no matter how small a hardware or software change can be, it's still extremely expensive, especially as we move further down into a program's development cycle. So understanding that high cost of even small changes, we wanted to minimize it. So the Paragon incorporates much more reconfigurability than in computers of the past. So instead of, for example, using analog signal demodulators, we use high-speed sampling and do the demodulation in mathematics inside FPGAs and software, which allows us to change how a signal is managed without changing hardware or software. So the Paragon incorporates this flexibility via a multitude of what we call parameter data items, where effectively the end user just enters configuration constants into a table, and then the Paragon automatically treats those input signals according to what that function that table says. So this reconfigurability also includes major configuration items such as how many CPUs are installed, as well as other situations like are you multiply redundant on the aircraft? Are there 3 computers, triplex redundancy, 2 or 1 computer? So the reconfigurability allows the end user to reconfigure the Paragon without the need for hardware and software changes, and the end user simply updates these parameter tables to have the box automatically reconfigure. So those are, I'm going to just wrap it up again: sheer increase in horsepower, common mode failure mitigation, reconfigurability without having to change hardware and software are some of the key prominent features of the new Paragon.
Great, thanks, Steve. Another question we have here: what is the Army's acquisition strategy for these components? Does the Army pick and choose components for each aircraft, or do the aircraft manufacturers choose the component providers? Are there active solicitations for these FVL components right now, or are they upcoming?
Harold, would you want to take a crack at that one?
Yeah, sure. Look, I can. That's a pretty complex question, but it's a really, really good question. So I'll say that all the things that were mentioned there are kind of all in play today. We're definitely seeing solicitations from the OEMs as they look to fill out their teams for how they're satisfying the requirements for future vertical lift. And right now, FLRAA is kind of front and center because of the timing of that program. But what makes it complex is you have multiple OEMs and also the Army who are also weighing in on procuring these components. So we're having to pay attention to all the different avenues that are in front of us right now. We see that we think eventually the Army will select and choose things that they're calling crown jewels, that they will procure themselves and manage themselves to be common across the fleet. And those are things that are probably, higher value, more complex things that they would want to be common and be able to manage in a single way and not be unique to each platform. So I don't know if anybody else has anything they want to add to that, but it's a really complex environment right now.
Yeah, and maybe I'll just add to that, Harold. I think that's, like we mentioned in our presentation, that's why we think it's really critical to be engaged with the Army and with the primes, just because it is such a dynamic environment. And we know that some of the strategies aren't necessarily set yet. And so we really have to kind of work and evolve with the strategy as it evolves across, through the program and as it matures. So that's a great question.
And I guess we got a follow up to that one. Harold, what would you characterize as the crown jewels?
Another really good question, and I'll say that I think the Army has created a list. They've not shared that list with us yet. I think from our perspective, things like things that have been traditionally procured by the Army, like aircraft survivability equipment. The comm equipment, since those all have to be interoperable as well. Those things make perfect sense. We also mentioned, here that the Army really is front and center with them is their modular open systems approach. So we think there needs to be a common MOSA. That's something that the Army is defining in their what they call their FBL architecture framework. So that's a really important artifact that we're all contributing to right now to try to ensure that MOSA is common and interoperable across the fleet. So I think it's a really important component of it.
Great. Another question we have here, can you define systems, integrated structures, and their advantages?
Yeah, maybe we'll go to John from our aerostructures business. John, can you maybe talk a little bit more about what you guys are doing from an integrated structures perspective?
Yes, thanks, Luke. So right now, or historically, aerostructures has a proven track record of providing various flight control surfaces using different technologies, both metallic and composite, on fixed wing fighter aircraft, including F-15, F-16, A-10 as a few examples. A few years ago, understanding the need to offer the warfighter with lighter and lower life cycle cost structures, we started the process of switching from metallic to composite, including out of autoclave type manufacturing processes, which led to our recent F-16 horizontal stab using a resin pressurized mold out of autoclave cure manufacturing process. Taking that to the next level, what we're now working with our mission systems team is to take advantage of that real estate that's literally inside of these flight control surfaces, whether it be a horizontal stabilator, a vertical, a stub wing, a weapons pylon, and determining how best to take an antenna and literally build it inside of the flight control surface so that we can totally eliminate any drag of the antenna which may have been flying on the outside of the aircraft. Also looking at doing the same thing with lighting. In fact, over 20 years ago, aerostructures embedded navigation lights on the wingtips of our Gridlock F-15 aircraft wingtips. Very smooth surface. There was actually no drag because the navigation lights are literally embedded inside of the wingtip itself. So we're doing that same process with a new VHF antenna that we'll be testing at the end of the year to prove out that we can literally reduce drag by taking various types of systems that may hang off the side of the helicopter and embed them in the structure itself. Not only inside of the free real estate that we have, but also what can we do to embed things in between the plies of the composite material. So we're pretty excited about this, and we'll have some proven results here in Q4.
No, thanks for sharing that, John. And I think that's an area that we're all excited about, and a lot of work being done across our different business units in this area. And it's definitely an area we're investing in. to support this weight and drag conversation. So thanks for sharing, John.
Yeah, thanks, John. And just a reminder, if you have a question, please send it to me over chat. We're definitely getting some good ones here. Another one, Luke, the U.S. Army has challenged industry to develop a solution that will rapidly respond to emerging threats. What's Collins' approach to integrating best of industry mission capabilities?
Yeah, so that's a great question, and definitely something that we're very focused on and kind of in the middle of here very recently. And I'd like to pass that question over to Mike Riley. And Mike, maybe you can share some of the things we're doing from kind of a mission systems integration perspective to kind of support that topic.
Sure, Luke, thanks. It's a great question. And again, happy St. Patty's Day to everybody. Our approach is enabling, encouraging, and simplifying the implementation of third-party content, draws upon our successful implementations of both our aerospace and our IT sectors. We've built just recently, we've completed a customer experience center here in our Huntsville facility, and we're inviting industry partners to bring forth solutions and integrate into our architecture with a rapid prototype environment. Essentially, we're providing toolkits, training, a sandbox environment built upon prolific open standards for our mission capability providers to design, prototype, demonstrate, and fully integrate their capabilities. The benefit to the third party is that Collins' core architecture framework properly isolates the complexities of safety critical development from the third party mission capability, which reduces their overall development burden, ensures system consistency, and simplifies system certification impacts. The benefit to the USG, obviously the government, is lower costs, faster mission capability integrations and iterations from more providers, and ultimately gets things to the warfighter faster. So I hope that answers your question, Luke.
Mm-hmm. No, thank you for that, Mike.
Okay, we've got another one here, Luke. Can you talk a little bit more about the lighting solutions and weight savings associated with them?
No, absolutely. That's a great topic. And maybe Joanna, do you maybe want to share a little bit about what we're doing in the interiors business in that area? Check your mute. Yeah, there you go.
Sorry, I'm double muted. Yeah, good afternoon. Doing a bit from a lighting perspective in terms of weight savings and also drag, as John just mentioned here a little bit ago. By combining lights, for example, that's another way that we're reducing savings. We're able to put those, two pieces together that does, a weight savings, for us as well as drag. We're also doing some flush mounted lighting as well. So we've been also looking into, like John had described, antennas and lighting together. So there's some combination things that we can do that would, it definitely with, light with weight, there's a savings, but I think drag is probably a little bit more impactful, I would say, just because of those structures on the outside of the aircraft now coming in and being embedded, flush mounted, as well as that combination. So we see a little bit more of that savings on the I would say on the drag side than on the weight side per se. The weight side, I think you saw a lot of what we can do from a seating perspective. That's really where you're going to see a massive, I think, weight savings is on that technology that we provide. A very good question. Thank you.
Yeah, and maybe Preston, would you maybe want to comment? It kind of ties into that question. Maybe some of the things, maybe a little more detail on the antenna side and some of the work we're doing there with the lighting team.
Sure, absolutely, Luke. As Joanna mentioned, a big goal for us was to integrate antennas into the aircraft in ways that didn't create a lot of parasitic drag. As we look at the communications, the connectivity requirements for platforms like FARA, there were on the order of 35 to 40 different antennas that might be required on that aircraft. You can't have a flying Porcupine that goes 250 knots and has the range requirements that FARA is going to have. So we've really taken a holistic look as we have built our FlexLink system to be able to use antennas for multiple purposes. So some of that, and along with that, integrating them into the aircraft in a way that reduces or completely eliminates drag. Another example would be a requirement for a beyond line of sight backup to SATCOM using HF. Typically, HF antennas are something that are very difficult to integrate into an aircraft unless you have a lot of real estate. So we've taken some novel approaches to create NIVIS antennas for these aircraft that allow them to communicate beyond line of sight using HF radios in the advent of a loss of SATCOM capability, and integrating that into the aircraft in a way, in a vertical stabilizer that allows it to be, have a good launch angle and receive angle and still communicate over significant ranges. That's just one example.
Yeah. No, thank you, Preston.
Thanks, Preston. We have another question about the new Pegasus hoist that was mentioned. Can you talk a little bit more about what makes that better than your previous offerings?
No, great question. Richard, would you like to take that one?
Sure. Yeah. So we're seeing, I think, a sea change in hoists of technology that's been around for 30, 40, 50 years. And we're seeing changes across all parts of the hoist, leading to increased capability, higher capacity from a load perspective, higher speeds, specifically at maybe lower loads where you only have one person on the hoist. And finally, the maintenance and operational readiness of the systems go into a modular system that enables rapid repair and swap out if needed in the field. So avoiding any situations where the hoist is not ready for service and operation.
Great. Well, I think we've got time for one more question. You mentioned FlexLink. Beyond its weight and drag reduction, what capabilities make the radio different?
Oh, great. Another great question. And Preston, you maybe want to talk a little bit more about what we're doing to pull that whole FlexLink system together.
Sure, absolutely, Luke. Yeah, that's a great question. Beyond meeting the weight and drag reduction goals for FVL, we really had a couple other main objectives as we developed FlexLink. The first, I would say, is to architect an open system that allows platforms to upgrade their capabilities fast enough and at an affordable cost to be able to keep pace with changing enemy threats. We see in the marketplace and in the battlefield every day, technology is evolving at such a rapid pace now, and our enemies are taking advantage of those rapid advancements in technology. We have to be able to respond quickly also if we're going to be able to keep pace with those threats and keep our systems up to date and protected against those threats. So that means you need to be able to upgrade, without significant recertification time and cost. You need to be able to integrate skills from third parties as they are developed, and you need to be able to provision for future capability growth. So all of those things were tenets that we took to regard as we were developing the FlexLink system. So it's designed in a way that, there's enough modularity in it and separation between multifunctional processors and multifunctional apertures to allow you to integrate those new skills, those capabilities quickly. The other big area is in mission capabilities. If you look at the FVL platforms, they will need an unprecedented level of connectivity. The multitude of networks, the simultaneity requirements, and the robustness and resilience requirements for those platforms are all very challenging. And all of those demands were considered as we designed FlexLink. So, addressing all those myriad of requirements really drove us to take a completely new look at the architecture of, what we might have considered a software-defined radio. Still software-defined, but basically designed in a way to allow those rapid upgrades and to make sure that we address the really challenging requirements of these future aircraft.
Great. Well, thanks, Preston. Thanks, Luke. Thanks to all the panelists, and thanks to everyone who joined today. We really appreciate the opportunity to speak with you about all the exciting things we're doing in support of Future Vertical Lift at Collins Aerospace. If you didn't get a chance to ask a question or you have anything that you'd like to follow up with us on, you've got Luke's contact here. Please encourage you to reach out to him and we'll follow up with you. And with that, thanks again for joining, and we'll see you next time.